Now, truth tables and logical equivalences are all well and good, but what we really want to get to are what are called rules of inference. If a statement P implies Q is a tautology, remember this will depend on P and or Q being compound statements of some form, then we say that the statement is a rule of inference. A tautological conditional statement, a rule of inference, can be presented in the following way. You list the hypotheses, and then you put this horizontal line with this triangle of dots and the conclusion Q. If the hypothesis is several things conjoined together, each of those things is usually given its own line. This isn't a strict requirement, but it is a convention. So for example, this is a tautology, P or Q, and not Q, implies P. The hypothesis is P or Q and not Q. Does that have a conjunction of several statements? Yes, it's the conjunction of this disjunction and this negation. So since we can have two statements conjoined together as the hypothesis, when we write it as a rule of inference, each of those things can be given their own line, as follows. As soon as you see it written like this, you would say P or Q and not Q implies P. Or P or Q and not Q, therefore P. This triangle of dots is frequently spoken out loud as therefore. Now, how do I establish a rule of inference is valid? In other words, that the conditional statement that it creates or represents is indeed a tautology. You can do it with truth tables. Okay, you can always just make a truth table for whatever the statement is. So here's a rule of inference. P implies R and Q implies R and P or Q, therefore R, does represent the following conditional statement. It is a conjunction of three separate things, so I have this and that implies R. You could make a truth table for this and show that you've made a tautology. But that's going to take a while. It could be very time consuming. We're going to be introducing a new way of establishing that rules of inference are valid. In other words, that conditional statements like this are indeed tautologies, always true. And we're going to rely on invoking known logical equivalences and rules of inference we've already established. If I've already shown something is true, I can use that as a single step later on. And this is known as two-column proof. Okay. So let's first take a look at what are known as givens in a two-column proof. So a two-column proof, yes, has two columns. The left column is going to be used for writing statements with a line number. I actually put the line numbers in their own column, but no one ever calls it three-column proof. The line numbers are just a way to keep track. The right column is used for what justifies the statement you just wrote. And justifications are not a matter of you writing an essay to convince your reader. No, there are a specific list of allowable things, and only those things may be allowed. You can't just make it up as you go. You are a machine executing a predefined list of commands that are allowed at any particular step. The proof overall is completed when the conclusion of the rule of inference is stated and justified. Remember, a rule of inference is a conditional statement fundamentally. If you can get to the conclusion and justify it as true, then you're good. But every line must be justified, so we need to establish what the allowable justifications are. The most basic one, which is used in 98% of two-column proofs out there, is where whatever those hypotheses were in the rule of inference, you can put the hypothesis into the two-column proof and justify it as a given. So here is the rule of inference that we introduced on a previous slide. You can introduce each of these hypotheses, P implies R and Q implies R and P or Q, each of them may be introduced, justified as a given. Because this is exactly what shows up there. This is exactly what shows up there, and P or Q is exactly our third given. Now you have to do some very mysterious things. We really don't know yet what can happen, but we know where we are trying to end up. If R can be stated and then properly justified, the proof overall is complete. Whatever these hypotheses are, state them and call them givens. Then a mystery occurs, but you know you are trying to get to your conclusion. And once that's been justified, your proof is complete. Another thing we can do to introduce statements into a proof is what is called a tautology introduction. So far we can't do anything. All we can do is state our givens, and then we're out of steam, because it's the only justification we know, and it's only allowable to actually put the givens in there. Okay. There are other things we can do, and the simplest is tautology introduction. The justification can be abbreviated as plus T. You are adding a tautology. Tautologies are always true. That's what makes it a tautology, which means you can always invoke it as part of a proof because you know it's true no matter what. It doesn't depend on what particular points you've already raised in your proof or what other justifications you've used. Since a tautology is always true, you can always introduce them. Some tautologies have names, such as law of the excluded middle or the law of contradiction, and it can be helpful to introduce them with that name so that your reader can follow along. So for example, in the proof that we were attempting, we have our three givens, and we know we're working towards this conclusion. Take a look at this line here, P or not P. That's the law of the excluded middle. P is true or P is false. This is a tautology, and this is the law of the excluded middle. So I can introduce it by justifying it as, it's a tautology, I'm sticking this in. P or not P is always true. I still don't know how to go after this though. And just because I've introduced it does not mean it's useful to do so. Okay, there are two things you should ask when putting together a two-column proof. The thing I'm doing, is it allowable, and does it help? The first question is more important. Okay, it is much better to do things that are allowed but not helpful versus doing things that are potentially helpful but not allowed. Okay, we want to be very strict at how the rules of logic and rules of inference can be used. So first, before anything, worry, is this an allowable step? So even though in this case I don't necessarily know that this is going to help me, I do know that it's allowable. I can stick a tautology in. Of course, I can do lots of other tautologies. I could have introduced, for example, R or not R. I could have introduced P implies R or not P implies R. This is still the same tautology. Okay, notice what I have is a statement or its negation. This is still the law of the excluded middle. I could even do something convoluted like the negation of P implies Q or S implies T, or the negation of P implies Q or S implies T. Because what have I actually claimed? A big mess or its negation. That's still the law of the excluded middle. It's allowable, it would be totally useless. Okay, there would be no point in introducing it in this proof, but it would be allowed. All right, let's talk about something known as substitution, which we've already kind of hinted at. So suppose you have a statement and it's a tautology and it has a literal in it for the sake of argument P. The statement will remain a tautology if every instance of P is replaced with some other statement, not necessarily a literal. Because tautologies are always true regardless of their component pieces being true or false, if you completely replace all of the P's with something else, this is called substitution. Okay, the notation is a little tricky to get a handle on at first, but it's just this square bracket referring to a line number. And this can be interpreted as, in line number n, I'm replacing all instances of P with Q. So here is an allowable sequence of rows, not necessarily helpful, but yes, allowed. All right, P implies P, that is a tautology. Okay, it's usually given as an exercise that it should be something you can establish with a truth table. P or not P is a tautology. It's the law of the excluded middle. So both of these can be introduced. Now let's take a look at line 3. It says Q implies Q. Well, maybe I haven't built a truth table for this, but I did build a truth table for P implies P. So what's the justification? In line number 1, take all instances of P and replace it with Q. So yes, in line number 1, which we already know to be true, take all of your P's, replace them with Q's. Sure. Now let's look at line 4, which is a mess. What does it say? In line number 2, which we already know to be true, take all instances of P and replace it with the compound statement Q implies R or S. So instead of P, I put Q implies R or S, or the negation of Q implies R or S. This is not useful, but it is allowed. This is simply performing this substitution on the known true statement given in line 2. So notice that these line numbers are very useful in justifications of certain types. Tautologies can be introduced and they have nothing to do with anything else that's going on. But where did this line in 4 come from? Your reader can now understand that in line 2 we perform the following substitution, and that's how you end up with this. So that's what the second column is for. The justifications so that the person looking at your proof can understand what's happening. Okay, and as we've mentioned, the statement that you're substituting into the tautology doesn't have to be a literal. It can be any statement at all. In line 3, we substituted one literal for another, but in line 4, we substituted the literal P with a statement Q implies R or S. Okay, I could actually then go ahead and do another substitution on line 4. I could, for example, replace all literals R with P or R. What would happen then? I'd get Q implies P or R or S, or the negation of Q implies P or R or S. All I've done is go back to line 4, find all instances of R and replace them with P or R. So in this line, anywhere I saw an R, I simply replaced it with a P or R. And this is the principle of substitution. Okay, it's a basic rule, and we frequently do it without mentioning it. So for example, most people, myself included, would actually be fine with line 4 being introduced as tautology introduction. It's pretty clearly a statement or a negation of that statement. Similarly, line 3 isn't really any different than line 1. So even though this may be the statement that you actually have a truth table for, P implies P, and you never bothered to make a truth table for Q implies Q because what would be the difference? Okay, very few people are going to be so pedantic that they require you to say, here's the statement we have a truth table for, and now do the substitution. Most people, such as myself, would be fine if you simply said this is a tautology, or this is a tautology. Because the way it's written, it's very clearly something or its negation. So it's definitely the law of the excluded middle, just with an implicit substitution that we don't really bother listing out as a new line. Let's come back and talk about logical equivalences. So a logical equivalence is, remember, two different tautological conditional statements. So what it does is it gives you two rules of inference. Okay, so for example, here was associativity of disjunction, a logical equivalence, that we've already discussed. So that means that I have two separate conditional statements that are tautologies. P or Q or R implies P or Q or R, but also a tautology is P or Q or R implies P or Q or R. Okay, a biconditional statement being a tautology, because it is a conjunction of two conditional statements, is the same thing as saying each of those conditional statements were tautologies. So depending on which order you interpret them, you can get two separate rules of inference. Okay, these look similar, but they are different. Notice this is saying that P or Q first and then R implies Q or R first and then P, and this is exactly the reverse. This conditional statement as a tautology can be written as a rule of inference like this, and this tautological conditional statement may be written as a rule of inference like this. So anytime you have a logical equivalence, you have two separate rules of inference that it can tell you. Both of these rules of inference would just be called associativity. When you have a logical equivalence, even though you get two separate rules of inference, you actually use the same name for them because you can go back and forth. Okay, so all of the logical equivalences that we introduced in a previous video, commutativity, distributive properties, De Morgan's laws, double negation, and so forth, all give you a whole bunch of rules of inference, and you use those names to refer to them. So we have a bunch of rules of inference, these logical equivalences and other things. How do we use them to construct proofs of other rules of inference? So if every hypothesis of a known rule of inference occurs as a valid line, possibly including some hidden substitutions, then what you can do is you can write the conclusion of that rule of inference using the same substitutions. The justification for this line, remember every line you write has to be justified. If you're using a rule of inference to put in a new line, you justify it as that rule of inference plus referring by line number to each of the hypotheses that you're using. So if a rule of inference has a certain number of hypotheses, that's exactly how many lines you have to refer to. So let's see an example here. Now in line 8, let's just pretend that that line was somehow justified. In line 9, we are supposedly using the distributive property on line 8. Now there were a bunch of things that were called distributive property, but one of them was the following. P and Q or R is equivalent to P or R and Q or R. So if I write that as a rule of inference, I could say the following. P and Q or R, therefore, P or R and Q or R. Now I don't quite have this hypothesis, P and Q or R, but I do have P and Q or something. So if I use this with the substitution, replacing all R's with P implies Q, we would get the following. P and Q or P implies Q. Remember, I'm replacing all of my R's with this. Therefore, P or, well, not R because I'm replacing it, P implies Q, and Q or, not R, but P implies Q. And that is exactly what is written here in line 9. So we took one of our distributive properties, interpreted as a rule of inference, including a substitution. I now refer to this line as the hypothesis in line 8. And since I have this hypothesis, I am allowed to write this conclusion. So I have written that conclusion justified by saying I applied the distributive property to line 8, and that's exactly what we did. So the relevant distributive property has one hypothesis. That's what we referred to, including a substitution, and then we applied that equivalence to get the new line. This will be very awkward at first, but it will make more and more sense the more you practice. Okay, and as we create new rules of inference, the benefit of this is we get to give them names, and then we can use them to derive even more. This has a mushrooming effect where the more we prove, the more tools we have at our disposal to prove new and new things. Now we're going to introduce a few rules of inference and work through their proofs. And what we're going to do is we're going to understand how they operate so that we can use them to derive future rules of inference. First up is this. Now, the fact that this statement is a tautology can be proved using a truth table. We are going to omit that. Remember, all of these can be done with truth tables. Once the statements get sufficiently complicated, it becomes unwieldy. But for this, it's not that bad. There's only 2 literals, so it's only got 4 lines in it. You could use a truth table, show this as a tautology. So I interpret it as the following rule of inference. It's got 2 hypotheses conjoined in a single conclusion Q. So if P implies Q and P, therefore Q. This is known as modus ponens. It's just Latin for the method of affirming. And what it says is, P implies Q is a true fact. P is also true. Now, if a conditional statement is true, one way that can happen is for the hypothesis to be false. But we are asserting that P is known to be true. So if P is true and the conditional statement is true, based off the truth table of how conditional statements look, the only way for P implies Q to be true and P is true is if Q is also true. If P implies Q and you have P, you must also have Q. Modus ponens, notice, has 2 hypotheses. So if you want to use modus ponens in the proof, you need to refer to 2 lines, and you can abbreviate that as MP for modus ponens. Now the 2 lines that you refer to are not just any 2 lines. It's got to be a conditional statement and something that is exactly the hypothesis of that conditional statement. The two lines you refer to have to be a conditional statement and its hypothesis. Otherwise, you are not correctly using modus ponens. And the line that you get out has to be the conclusion of the conditional statement you referred to. These have very, very strict requirements so that you don't accidentally think that logic tells you things that are wrong. Okay, you have to refer to a conditional statement and its hypothesis, and what you get out is the conclusion of the conditional statement you referred to. A very related rule is known as modus tollens. Again, from a truth table, you could show that this statement here is a tautology. It's got some negations thrown in, but it really still involves just two literals. Interpreted as a rule of inference, here it is. If P implies Q and not Q, you must have had not P. So the conditional statement being true, but the conclusion being false, means that the hypothesis could not have been true. And if it's not true, it must be false. This is called modus tollens, okay? And again, the intuition is if P must imply Q, but you don't have Q, you couldn't have had P, because if you did, P would have implied Q, which you know for a fact you don't have. Okay, this is called modus tollens. You can abbreviate it as MT. Very much like modus ponens, you refer to two things, a conditional statement and the negation of the conclusion. It must be very precisely whatever the conclusion is, negated. And what do you get to conclude? The hypothesis, negated. Okay, some people get this wrong and they think that not P will imply something. No. It's a conditional statement and the negation of its conclusion, and what you get is the negation of its hypothesis. That's the only way you can ever use modus tollens. So let's take a look at a rule of inference and prove it. Now here is all the space we're going to need. Okay, trust me, this is all the lines we need, and some of the justifications are given or at least partially given. Let's try to figure out how we can complete this proof. Notice that the justifications for lines 1 and 2 is just given. A given is one of the hypotheses of the rule of inference. So the only things I can put here are the individual hypotheses, P implies Q. P implies Q implies not Q. Okay. I could put them in the other order, that's fine. I could even repeat one of them, but it stands to reason that I probably need both of these in here if I want to get to my desired conclusion. So go ahead and state each line here, your conjoined hypotheses, they get their own line justified as givens. Also, the proof is complete when the conclusion not P appears. So I happen to know the last line is going to be not P. How is it justified? I don't know yet, this proof is not done. But I do know that when I make a not P show up, I'm going to be done. Let's take a look at line 3. The supposed justification we're going to use is modus ponens. Modus ponens must refer to two lines, and they have to already exist. So if line 3 refers to two different lines, it had better be lines 1 and 2. So I'm going to combine line 1 and 2 using modus ponens. Now modus ponens refers to a conditional statement and its hypothesis. Could line 1 be the conditional statement? Sure, it's a conditional statement, P implies Q. But if this is my conditional statement, the other line I refer to has to be its hypothesis, which is P. I don't have a line that just says P. And also don't think I have the line not P. This line doesn't really exist yet. Okay? So if I refer to this as my conditional statement, the only hypothesis I could possibly refer to is P, and that doesn't exist. So that can't be how I'm using modus ponens, which means line 2 has to be the conditional statement. And it is. P implies Q implies not Q. So I do have a conditional statement. What's its hypothesis? This entire thing, P implies Q, which is exactly the other line I'm referring to in line 1. So the conditional statement is line 2, and its hypothesis is line 1. If I'm applying modus ponens by referring to a conditional statement and its hypothesis, what I get out is its conclusion. So if the justification for line 3 is modus ponens on lines 1 and 2, the only thing I can be getting out is not Q. By referring to this conditional statement and its hypothesis, I extract its conclusion. So now, what can I do to get out a not P? Well, here's a hint. I'm going to refer to lines 1 and 3. If I'm referring to lines 1 and 3, I'm referring to a conditional statement and the negation of its conclusion, and what I'm hoping to get out is the negation of its hypothesis. From this conditional statement and its negated conclusion, I extract its negated hypothesis. That is exactly the rule, modus tollens. So from the top, I state the two givens. Here they are. By combining this conditional statement with its hypothesis, the overall statement P implies Q, I can extract its conclusion, not Q. So whenever these two statements are true, this one must be, because I used a rule of inference, which is a tautological conditional statement. But whenever these two lines are true, this one is also true by using this tautological conditional statement. This is the power of using rules of inference. If you have lines that are true, and you have rules of inference, which are conditional statements that are always true, if their hypotheses are true, their conclusion must be true. So using rules of inference allows you to write a chain of further and further true statements until you hopefully get to what you were trying to at the end. So now we know if you ever have P implies Q, but you also have P implies Q implies not Q, you can extract not P. But remember, you can combine these with substitutions. If you have a conditional statement and that conditional statement implies the negation of its conclusion, notice that this Q is the same as these. So conditional statement implies negated conclusion. You also have the conditional statement. You must be able to extract the negation of the hypothesis of the first one. Okay, you could refer to this by name. It's not going to be something we're ever going to use again, I don't think. But you could give this a name. For example, you could call it something like, remember, this is now a tautology that we've shown to be a tautology, which makes it a theorem. So you could call this theorem 1. And if everyone, had the same reference book you did and knew that this was called theorem 1, in a further problem, you could use this as a justification. You could say theorem 1, referring to how many lines? Well, if you want to use this rule of inference, because it has two hypotheses, you'd have to refer to two lines. One of them would have to be a conditional statement, and the other would have to be another conditional statement, whose hypothesis was the first one and whose conclusion was the negation of the conclusion of the first one. And then what you could extract was the negation of the hypothesis of the first conditional statement. Okay, and this is all a lot to take in the first time through. Practice will help, and the real power we're after here is the more you do these things, the more you realize it's the same building blocks just being combined in marginally different orders to generate things that look complicated, but is really just saying, well, if X, Y, and Z are true, then Z must have implied A is true, so I can extract this and then I can move to that. You're just following existing known steps to generate more complicated problems. Rather than re-deriving the entire complicated thing every time, you're leaning on the fact that you've already done some simple stuff so that you can go step by step to make a more complicated thing appear without very much work. That's the true power of rules of inference and mathematics in general.